rest of this chapter, I will just go over through some of those kind of concepts which I consider to be very important in the future, and also some of the parts which I consider to be kind of a little bit tricky. So just for the rest of the material, I would just require you folks to study the lecture notes, read the textbook, and then do plenty of those kind of homework, and then just catch on. And of course, if you do have any questions, you can of course always check with me to clarify any confusion you have. Okay? But I do require you to spend significant time self-studying this particular chapter. Okay? So for this section 6.4 on the polar reactions, we will go through some of those kind of terms which are important. So very first, the terms is about polar. What really is polar, and which is the adjective, and the noun for it is kind of polarity. Okay. So there's a more detailed definition in the textbook, so you can just find out in the textbook. But one thing I would really want to mention is that whenever we talk about polar, we're just talking about the properties which are associated with the charged ions, or we could have neutral compounds. But those neutral compounds, they could have just charged ends. So we have the separated ends. So such as one good example would be amino acids. So this is one of those kind of natural molecules which make up the proteins in our body. Okay? So when we think about amino acid, it has one part which is called ammonium group, so which is positively charged, where we have another part which is called a carboxylate, a functional group, which is actually a negative charge. Okay? So overall, the amino acids are neutral, but it does have the charged ends. So those molecules will also be polar. Okay? So this first is about the polar and polarity, and then we think about just because polar reactions involve the charges, and then just how do the charges interact with each other. So this is something basic from the physics. So it's pretty simple. Okay? The idea is that the same charges, they always repel each other. If we do talk about two of the positive charges, or if we do talk about two of the negative charges, they always repel each other. In the case of negative versus negative, such as if we do have just two electrons, they're gonna repel each other. Okay? So that's about the basic interaction. And on the other side, if we do have the opposite charges, such as one positive, one negative, and then they're going to attract each other. So this is actually how the ions will interact with each other, and that's our basic principle. Okay? So based on that, and then we'll have some additional definitions. The first thing is nucleophile. So what really is a nucleophile? We look at the word by itself. Okay? So I just underline over here the phile. Phile just means like. Okay? So if you think about some other word, just you may have heard about, such as hydrophilic. So if we do have the word hydrophilic, you probably know that it's something which likes water. Such as if you have table salt, if you have sugar, those molecules, they like water, they rapidly dissolve in water. So they are called hydrophilic species. Now for this kind of nucleophile, it is something that likes nucleus. Okay? We put the things together, nucleus and the phile, nucleophile. Okay? And then we think about what really is a nucleus. So that's back to the atomic model we talk about. The atoms that are made of nucleus and electrons. And we look at the nucleus. It is always made of protons and neutrons. Neutrons, of course, are neutral. They have zero charges. On the other hand, however, the protons, which is essential element, which is the essential component of the nucleus, one proton does have one positive charge. Okay? So because of the protons are charged, the nucleus is positive charge. And then we think about this basic principle, since the nucleus is positive charge, for something to like it, so that something has to have the negative charge. Or what is really negative charge? Well, electrons have negative charges. Okay? So basically for the nucleophiles, it must be an electron-rich species. It is most commonly negatively charged species, ions. Okay? So actually we will say that any ion, such as chloride, bromide, hydroxide, or just any of the ions you can think about, all of them will be able to serve as nucleophile. Okay? But also some of those neutral compounds could also be nucleophile. I'm just giving one example over here. with this particular molecule, which is called the Masson law, to check for this particular compound. Oxygen in the middle has 2 lone pairs. So as long as we have those lone pair electrons, those species could also serve as nucleophiles. Okay? So in the polar reactions, nucleophiles will donate a pair of electrons, and then by the definition, so something which donates a pair of electrons, just check about those definition of Lewis acids and base before. So by definition, a nucleophile will also be a Lewis base. On the opposite end of this nucleophile has to react with something in a polar reaction. That something else is called the electrophile. Electrophile is totally opposite of the nucleophile. Okay? So first of all, of course, by the name, it is something that likes the electrons. So now because electrons are negatively charged, so in order for something to like it, that thing has to be positive or partial positive. So if something is positive, that means it's electron deficient. Okay? So electrophiles need to be electron deficient. They cannot have abundant electrons. They have to have very little so that they can begin to like more electrons. Okay? Electrophiles are typically positively charged. If we talk about the anion cations, positively charged kind of ions, and then all of them could be able to serve as an electrophile. Okay? But the point is that some of those kind of electrophile are also neutral. So here's one example of this particular compound, boron trifluoride. Okay? So this is one of the compounds we have just talked about before. And then back in the time when we talk about just orbital hybridization, I think we mentioned this particular compound. Look at BF3. So boron is actually group number 3 elements. It does have 3 valence electrons. And then note for this particular structure, boron shares 3 of its valence electrons with 3 individual fluorines. And then if you think about all the electrons around this boron, so actually we don't have 8. We only have 6. Okay? So for those elements, octet, of course, it's going to be the most stable structure. Since this one is 6, it actually will try to get more electrons to reach 8 if possible. So it's really this species is quite electron deficient. So BF3, boron trifluoride, it is indeed a very strong just electrophile. It really likes to attract more electrons. Okay? Basically, those are examples. When think about the general reactivity, electrophile will accept an electron pair in the polar reactions. So when we do have those polar reactions, the nucleophiles will react with electrophiles. And if you look at the definition, one thing that's kind of striking out is that we find out some of the neutral species could be nucleophile, and some other neutral species could be just electrophile. So I would say it's really depend on how those molecules react with each other. So even for the same neutral molecule, so it's possible for it to serve either as a nucleophile or as an electrophile based on the reaction. Okay? So I'm going to give you one example for that. So let's think about just 2 reactions of the chlorine. Okay? The chlorine element Cl2. Okay? So one reaction that the chlorine can undertake is that we take this kind of chlorine and we react with sodium. So the reaction here is actually just we balance it off. We find out after this kind of reaction will form the sodium chloride. Okay? So sodium is actually one of the very, very reactive metal. On the other side, chlorine is one of the very reactive long metal. So if you do ever mix these 2 together, sodium is a solid, chlorine is a gas. If you do ever put them together, there will be a huge explosion. Okay? So after the reaction is done, however, we're going to form some of the nice white solid, that's table salt sodium chloride we consume. Okay? So this reaction will proceed very just quickly. Now we check for this kind of reaction. Of course, sodium is a metal. What the metal do is that all the metals, they have a tendency to lose electrons. The electrons inside the metals are kind of free. So that's kind of property of the metals. Okay? So in this particular reaction, of course, sodium will become sodium ion plus 1, and then chlorine will become chloride, which is -1 charge. Okay? So apparently from here, we find out sodium is giving the electron to the chlorine. So if we try to analyze the detail of the reagent, so in here, sodium would be the nucleophile, where the chlorine will be the electrophile. this is just one reaction with chlorine, which does not involve any organic compounds. Okay. So how about some other reactions? So I'm going to show you folks one step which is involved in certain of those aromatic chlorylation, like just which is one of those kind of reactions we will mention in organic chemistry too. Okay. But here there is one step of that reaction. We can have chlorine reacting with iron chloride. Okay. So for that particular reaction, actually, like chlorine is a reagent, iron chloride is a catalyst. Okay. But how does the catalyst work? So this is actually the step. So chlorine will react with iron chloride. We form this particular species. So here we see something a little bit special. We have 4 chlorines around like the iron. So overall, this is one of those kind of like just polyatomic like anion, which has a negative charge. One thing that's very special is that we find out at least one of those chlorines becomes chlorine like a plus. So the name for this particular ion, we just call it chlorinium ion. Okay, so that's the name for this particular ion for the positive charge one. The point is that when we think about over here, like when we think about the region of the things, this Cl plus definitely will have to come from the like Cl2, the chlorine element. So here we have like 3 of this kind of chlorine. You just acquire 1 more, and it becomes like iron, like just tetrachloride, kind of just ion. Okay? So in this particular case, since we're going from charge of 0 for the chlorine to +1, so we find out there's increase of oxidation state. Effectively, of course, the chlorine is losing the electrons. So you have to lose the electron to have this increase in terms of the oxidation state or the charge. So in this case, of course, chlorine is effectively losing electron to the iron species. So in this case, chlorine will serve as a nucleophile. And then, of course, iron chloride will serve as an electrophile. Okay? So you find out this is just one example, and then just well, actually 2 examples of just different reactions with the same like just chemical chlorine. Okay? You find out based on what it meets, what is the other reactant, we're gonna have different like just outcome. Okay? So this is some of those kind of the terms I think will be like important to understand. Okay? So as an example for those kind of just polar reactions, like the textbook has just one example, which is kind of quite important, and also like that's part of like a reaction we will cover in the next chapter, which is alkene chemistry. So this next section will be about using the alkene addition reaction as an example for the polar reactions. Okay? So for this one, we have the addition of hydrogen bromide to isoline. So reaction proceeds like in this way. We have the isoline, which is double bond compound. Here it is a structure, and then we just have the HBr, hydrogen bromide. And then after this kind of reaction, so when you think about this alkene material, it has a sigma bonds. There's a double bond. There's 1 sigma. There's the pi bond over here. Okay? Sigma bond is very, very stable. However, the pi bond will be somewhat like unstable, so it can be broken. And once it's broken, we find out this is the final outcome. So 1 carbon will get H, a 2nd carbon will get Br. So if we do, this is the way to just think about how the reaction works. And then of course, many times we don't necessarily show all those kind of bonds. So we form this CH3, CH2, Br. So this compound is called bromoacid. Okay? So that is this particular reaction. Okay? So if you just look at it, apparently it's one of those addition reactions. We add this thing to the double bond, form a new structure, nothing is lost. Just we keep everything in the original structure, just put them together. Okay? People have studied this kind of reaction. We have tried to like just somehow make sense of it. So how do we try to think about the details about this reaction? We call the reaction mechanism, and then we try to move those electrons, and then just we try to like just make them work. Okay? This is one example of the polar reaction, and then just although it appears to be very simple over here, we just add 2 things together, we form like a new product. But indeed, people have studied this reaction, and we find out the reaction indeed takes place through 2 steps, and then just the very first step is that just we're gonna have a nucleophile and electrophile reacting with each other. So of course the task for us is to identify which of those species will be nucleophile, which will be just electrophile. So we just need to take a look at the individual molecules very carefully, and then how do we start off? We check the electrons. Okay, remember it's easier to find the nucleophiles because nucleophiles will be electron rich. So we check for the bromine. It should have 3 pairs. Okay, 3 lone pairs, and then just need to be further details for this particular just structure that we find out there's difference, of course, between the electron activity of the hydrogen and the bromine. So the hydrogen will have some partial positive charge, whereas the bromine will have some partial negative charge. Okay? So with that, we find out this is a species, so there will be some charges going on. When we look at the isoline, 2 of the carbons are the same to each other, and the hydrogen is a typical a lot really electronegative element. So when we look at this kind of structure, it's really neutral. So if you think about at least the possibility just being electrophile, just it's not that great. Okay? So, but the thing that so here we have to start off from something. We already found out bromine has plenty of electrons. So how about on this kind of other part, the carbons does not have lone pair electrons. However, as I mentioned earlier, the sigma bonds and there's pi bonds. The pi electrons, there will be 2 of them. So we have 1 bond, which is a pi bond. So those 2 electrons are called pi electrons. Pi electrons are also very reactive. Okay. So here, since we just get started, there may be something that you don't necessarily know. So here's one of the general case. Okay. If we have pi electrons, so this is something you may not necessarily know at this particular stage, but as you see more and more just organic reactions, you're going to gradually get that. Okay, so if you look at the halogen, chlorine, bromine, fluorine, iodine, and such in this case, we check for the bromine. So we have 6 of those kind of lone pair electrons in total, and also it shares 1 electron with hydrogen. So of course, the bromine has an octet structure. Without the octet, it makes it very much stable. So bromine or chlorine in general, when they do have those stable octet, so they don't really like to give those electrons out. Okay? And also in this case, even let's say it definitely could give it just out if the condition is proper. But over here, if it tries to give the electron to the kind of isoline, we already have some electrons over there. Electrons will dislike each other, so there's no point, or it's not possible for bromine to give the electron to the isoline. Okay. So instead, what will happen is that the pi electrons are more just reactive. So what it will do is that we're going to start from this kind of the pi electron pair, and we're going to throw that electron. Throw may not be the best word, okay? But those electrons will move to one of those kind of items. So now we just need to decide which particular just destination will those kind of electron pair move to. Okay? We have analyzed those charges just a moment ago. So what we find out, hydrogen is going to be partial positive, bromine is going to be partial negative, electrons are definitively negative. So negative, they are going to repel each other. So basically those kind of electron pair will never point toward the bromine. So it has to go to the kind of hydrogen. Just remember this basic principle we talked about earlier, opposite charges attract each other. So once this happens, then there's a lot of additional thing that has to kind of take place, because if nothing else happens, one of those carbons is going to form a bond with hydrogen. Hydrogen still have a bond with bromine. So hydrogen never have 2 bonds. So it always has to maintain this kind of 1 bond, have this valence of 1. So we just need to maintain that valence. So here, just quite often we move those electrons around. Okay. So one electron pair moves to the hydrogen, and then this electron pair between the hydrogen and the bromine will go to the bromine. So we find out our product will be something like this. this is our just intermediate. When look at it a little bit more carefully, and then just one of those carbons, because those two carbons are the equivalent to each other. So it doesn't matter which carbon gets the H. But since the electron comes from middle, one carbon gets the H, so we just assume it's the left one. So CH2 will become CH3. This other carbon will just be itself. CH2 and still CH2. So in the original structure, there are 4 bonds. Carbon is neutral. In this case, the carbon only has 3 bonds, 2 hydrogen and the carbon. So it will be 3 bonds only, and then electrons are going away. So this carbon will have positive charge. This bromine has more additional electrons, so it will be negative charge. So we have the bromide. So if you take a look at this, this is our step number 1. The isoline will be the nucleophile because it's giving out electrons. So of course HBr will be the electrophile. And then how about when we do have those 2 ions, how do we get to the final product? So actually that is quite easy. So for those kind of the bromide, if you draw out all the details about its electron, we'll find out 1, 2, 3, 4, 5, 6, 7, 8. Okay. So why do we have the elective charge? And actually bromine already have just 8 electrons around it. Normally the neutral bromine atom should only have 7. Okay. So with that 1 additional electrons coming from this bond breakage, it will just have 8 full octet, very, very stable. But also here, like just because it has 1 more than what it should have, so it has a negative charge. Okay? So negative, positive charge, they will really attract each other. So now in this particular case, the bromide will give out its kind of electron to the carbon. We form a bond. We get rid of all the charges. So that will be our step number 2, which gives us product. Okay? And then now we take a look at this step 2. Okay? Check its ions reacting with each other. So indeed we have nucleophiles and the electrophiles again. So in this particular reaction, we find out the bromide will actually be the nucleophile, whereas the carbocation here will be the just electrophile. So make sure you figure out those kind of details. We look at the bromine species. Here we have HBr, so that serves as an electrophile. Here we have Br minus, the bromide. Then now it will change its role into the nucleophile. So you need to take a look at those individual steps and then be able to figure it out. In this next section, 6.6, we will talk about how to use arrows, curve arrows, to draw the reaction mechanisms. So here are some conventions. This is actually one of the very important section. We just will talk about some of the basic just concepts. Actually, we have seen some of those arrows drawn in the previous kind of sections, but here we try to talk about just comprehensively. Okay, so this will form the basis for any of those organic reaction mechanisms we will talk about in the future. So make sure you can get fully understanding of this particular section. If there's any confusion at all, you should definitely check with me. Okay. So over here we have just some convention. We just try to think about any of the organic reactions. It's indeed the movement of the electrons. Electrons that make up the bond. If you think about a single bond, it's made of 2 electrons. Double bond, 4 electrons. Triple bond, 6 electrons. Okay. So once we move the electrons away from some particular location, that means that the bond will be broken. And then if at some locations where 2 atoms meet, and then the electrons move to the middle, and we're going to create a bond. Okay? For organic chemistry, that's all that matters. Bond formation, bond breakage, we form the new products. That's organic chemical reaction. Okay? And then how do we show those kind of movement of electrons? We just find out we just use these kind of arrows to do that. So the first type of arrow is the normal one, the full-headed arrow. So whenever I have this, we're trying to show that there is a pair of electrons that's moving. So when we do have a pair of electrons, of course we're talking about nucleophiles and electrophiles. We are talking about polar reactions. On the other hand, we could also have just a single electron moving around. So for that process, we use this type of single-headed arrow to show it. Okay? So if you look at the particular shape of the arrow, it really looks like a fish hook quite a lot. Okay? So if you do ever do the fission, and of course below you don't want to get a fish hook on your hand. Okay? So it will be painful. Okay? But we're just gonna borrow the shape, try to show the movement of the single electron. Once we do have this type of process, it will be called radical reactions. We have figured we have talked about that particular reaction in the previous section. So we talk about this radical reaction. There's initiation, there's propagation, and then there's termination. So there's other steps. Okay? For this current section, we will focus on the polar reactions, meaning we are going to talk about this type of just full arrows. We're going to move a pair of electron or two electrons always. Okay? So in this particular case, because we have to show the movement of a pair of electron, so of course the arrow must start from the electron. You want to move something, of course we start from that thing. Okay? So over here the arrow must start from pair of electrons, and then where can we find those electrons? It's either going to be lone pairs on a particular atom. So many of those atoms, such as sulfur, oxygen, nitrogen, so it's quite common for them to have lone pair electrons. So those the arrow could start from those atoms with the lone pairs. Or some other times it could also start from middle of a bond. Just remember, any bond, any single bond is made by two electrons. So actually we do have electrons available from the bond. Okay? So we could also start from middle of the bond. We're going to see some examples later. Okay? One thing very important is that we have those movement of electrons, so it will always cause some a change in terms of the charge. So here's the thing. So the destination where the arrow points to, it will always just gain one extra negative charge. Okay? And the origin place, the origin where the arrow starts from, it will lose -1 charge. Or in other words, if you lose something just negative, that means actually you're actually going to gain something positive. So you can see either the origin is either going to lose a -1 charge, or it will gain +1 charge. Okay? So that's some of the details of those charge the change. When you look at those words, there could be one thing that could be possibly a little bit confusing to you. So think about it while moving two electrons. Okay? So if you think about two electrons, suppose we should have one electron, one negative charge. Two electrons, we should have -2 charge. So why should we have those two electron movement and changes? Why the charge is not +2 and -2, but instead it's +1 and -1. So how do we make sense of that? Okay? So for that, actually, we just if we look at a few examples, I think we can solve that wonder. So think about one of the steps. If we do have HCl, hydrogen chloride, so without this particular chemical, when it's in water, it will dissociate. So it will just change into the proton and just chloride. So of course, proton can just further combine with water. It will form some ion, which is called hydronium ion. Okay? But just look at this process. Once we begin to just try to break it apart, and then we need to just draw out more details of the electron situation. So chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6. Here's the 7th one. The hydrogen just donates another electron. We form the covalent bond in the middle. So this is a Lewis structure for the hydrogen chloride, showing all those electrons. Okay? So now we think about this we start from pair electron, which is in the middle. This pair electron goes to the chlorine, and effectively, you see, hydrogen is losing its electron. There's no more. So we start from 0 charge. Originally, we get the +1 charge. On the other hand, although there is a pair of electrons moving toward this atom chlorine, but just remember, out of this pair, one belongs to it originally. Okay, so it does not actually obtain 2 more electrons. Just compare to itself. Just look at the dots. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, so the chlorine actually already have 7. It just obtains this 8th one from hydrogen. So it acquires 1 more electron than what it should have. It becomes the chloride. And of course, if you try to draw the full detailed electron situation for the chloride ion, we have 1, 2, 3, 4, 5, 6, 7, and 8. If you want to show the contribution, so see, we only have 1 more electron. Okay, so that's the case. whenever you just we do move a pair of electrons, but the charge always change by 1 instead of 2. Okay, so that's one thing you need to kind of realize. Okay, another point is that whenever you see the electric charge, just remember it will be equivalent to a pair of electrons. Okay, so again, this could be a little bit counterintuitive. So this pair of electrons should be 2, like elective 2 charge. Why should -1 charge kind of just kind of be equal to it? So the point is actually we can easily just see it with this chloride ion. Okay, so notice this chloride has elective 1 charge. It actually does have plenty of pairs. So for this chloride, it actually has 4 pairs that's going on. When we actually have this kind of polar reaction, and then what happens is that out of those 4 pairs, we normally will just use only 1 pair. Okay, so that's what I mean. Whenever you see the elective 1 charge, just remember there will be a pair of kind of electrons. So here we have chloride, and of course we could have some other species, such as like the oxide ion. We could have hydride ion, or we could have carbanion. Okay, elective charge carbon group. Okay, so for either one of those, so if you think about the hydride, it's not proton anymore. Proton is H+. Hydride is H-. So when we think about H-, there is a pair of electron. When we think about this carbanion, the electric charge carbon group. So what is the electric charge? That also means this particular carbon just have 1 pair. So 1 lone pair on it. Okay. So how about oxygen? Oxygen is a little bit special. In this particular case, we find out the oxygen only have 1 bond to the carbon. So it will have 1, 2, 3, 4. Think. Should have more. Yeah. So actually there should be a lot of just a pair. Okay. So we think about like the bonding situation. So when we think about for the oxygen should have 6 valence electrons. So let's use a dot to represent that. You see here we have 5 dots. 1, 2, 3, 4, 5. The 6th one should be forming the bond to the carbon, and then you see we have this X electron which come from somewhere else. So this oxygen is elective. Elective charge means a pair of electrons. So for the availability of at least a pair of electrons. Okay. So in those 2 cases, we just see each case we only have 1 pair. For the oxygen, we have 3 pairs. For the chloride, we have 4 pairs. Okay. So we're always using just 1 pair. Okay. So now we have some idea about this kind of the general concept, how the just charges kind of change around. So we're gonna go through some individual problems and also some specific examples. Hopefully that will help you understand those kind of the steps. Because once we put many of those steps together, that's our just reaction mechanism. That's how the reaction takes place. Okay. So when we have those kind of polar reactions, we always start from a nucleophile. Nucleophile will provide the kind of just electron pair. Okay. So nucleophiles are either going to be like a neutral or they're going to be more commonly like elective. So let's go through some of those examples so that we can better understand how to use a curved arrow to draw the reaction mechanism. So let's start with a neutral nucleophile. Okay. So here I have one example. We start from this particular compound, which is a methanol, and then just add a proton to it. This is rather simple like a reaction, and we can easily figure out which is a nucleophile and which is just electrophile for a simple reason. Oxygen is the only species in this. It's actually the only atom in this kind of 2 chemicals that has a lone pair electrons. Anything else does not have lone pair. Of course, we do have some of this kind of oxygen single bond, carbon oxygen single bond, carbon hydrogen single bond. But in general sense, single bonds tend to be pretty stable, so we don't want to break it in the beginning, if possible. Okay? So in this case, oxygen does have the lone pair electrons, and then we also have something positive. Electron positive, they are going to definitely attract each other. We have this kind of reaction going on. And then look at the process. So oxygen's electron is given to the proton, which means between the oxygen and the hydrogen, a bond will be formed. Okay. After this kind of bond formation, so notice where the arrow starts from, the charge will increase by 1. So we start from 0 for oxygen, we turn it into +1. Where the arrow points to, the charge will decrease by 1. So we start from H+, +1 charge, it decreases by 1, it becomes kind of 0. Okay. So when we take a look at the whole charge for the whole reaction. So starting material, it's 0 plus 1, positive 1. So for the product, it's just plus 1 by itself, still positive 1. So it is balanced. So just keep in mind, for any of those steps, the charge is always balanced. Okay? This is one example. Another one example just which is also related. So how about if we do have a neutral nucleophile, and then we do have a neutral electrophile to react. Okay? So here is that we have the same kind of methanol. So how about we have a molecule? Let's say what do we could have? So let's say we could have HBr. Okay. So let's think about the different molecule. This example is about like a neutral nucleophile reacting with just a cation. So just a nucleophile reacting with the electrophile. So as another example, so how about if we do have a neutral nucleophile reacting with another neutral electrophile? So as an example for that, so let's take the isolene, which is a double bond compound, and then we're going to add HBr to it. So actually I already talked about this reaction just a little bit earlier, just in one of the earlier sections for this chapter. Okay? But one thing that happens here, we have, well, I think we have all those kind of discussion already. So the pi electrons actually need to be more reactive than those lone pairs on the like just bromine. So this kind of get the electrons from double bond, or from the one of the double bond, from the pi bonds, which go to those kind of the proton, go to the hydrogen, and then this hydrogen bromine bond will break. So after this kind of reaction, we will form the carbocation, and we also form the bromide. Okay. So for here, like if we just check the principle we talk about, this is about the part. So a lot of the electrons coming from the middle of a bond. So not specific from, we don't know exactly which carbons. So if you think about it, so there's two electrons which are given out. So actually this first carbon contribute 1, the second carbon also contribute 1. So it's kind of like just electrons from middle. So what I will know is that one of those carbons will become positive charge. Okay? So after this reaction, so like just since two carbons are equivalent, so we just randomly put the hydrogen in the left carbon and this right carbon become positive charge. Okay? And then just notice for this kind of hydrogen, it's a little bit special. Notice we have one pair of electron moving toward it. So according to the principle, its charge will going to like increase by -1. So it has one more electron, it should become -1. Okay. But also there's another like a pair electron moving away. So it's kind of one moving in, another one moving out. Effective for this kind of hydrogen, it's going to be staying just kind of just neutral. So if you think about the situation over here, which will need to be more details of this kind of carbocation, you find out here is this thing. Okay? This hydrogen comes from this particular hydrogen. This hydrogen is neutral. This hydrogen, it is still neutral, forming one bond. Okay? How about for the bromine? The pair electrons move to it, so of course it will become negative charge. Okay? So we'll make sure like we draw those mechanisms, figure out where the arrow starts, where it points to, and also take care of all the charges. And then very likely you're going to get it right. Okay? So in this particular case, just always also pay attention to this kind of balance of the charge. Here we have 0. Here we have another 0, total is 0. Here we have +1, here we have likely 1, total 0 again. Okay, so the charge is balanced. Okay? So that's one example. There's another example which we will also actually see in the future, and that's actually it's a little bit special one. So I'm going to show you folks one of the process. So let's take the same kind of alkene, and then now instead of using this kind of HBr, so how about let's use Br2. Okay? So this reaction is a little bit special. And then here we just need to draw a little bit details of the electrons on the bromine. So we'll find out 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So this will be the structure for the bromine. Okay? For this particular reaction, which we will learn about in the future, so there is this first step is that when the bromine adds onto the alkene, so first of all, the pi electrons will come up. It will really begin to attack this kind of the bromine, one of the bromine. Okay. Once we do that, as what normally happens is that this kind of bond over here, it just moves and then just see very similar to the top case, and one pair electron coming in, another one pair with electron coming out. Okay, but for this reaction, there just need to be a special thing that this bromine also has it has plenty of lone pair electron. So what it can do is that over here, there's a third arrow that's going on. So we have something like this. Okay, so this makes it need to be complicated. But what I really try to mean over here is that if you look at the process, notice this particular first arrow means one of the carbon will form a bond with the bromine. So let's assume it's going to be the left carbon. So we'll form this particular structure. The bromine is going to form a bond to the left carbon. And this bromine also have just an electron pair moving to the second carbon, which means it will form also a bond with another CH2. And of course, we start from a double bond. One bond is going away. We should have the single bond. So we should have this structure. And that's for that kind of particular bromine. And for this kind of other one, it should be very simple. So just similar to the top case, of course, we are going to have the bromide. Okay? And then if you just try to balance this kind of the charge of everything, so here we have 0, 0, total is 0. Here we know the bromide is active 1, so that means, well, the species we have here, one of them should be plus. Okay? Which one is plus? It's quite easy to figure out. CH2, CH2, both of those kind of carbons have the correct valence of 4, so bromine should only form one bond. Here it has 2, so it has the positive charge. Okay? So that's the way to figure out the charge based on the balance of the charge. Okay? There's another way to look at it. So, and then that way is that you think about this kind of bonding situation. Notice for this kind of bromine, we have one pair or one arrow moving toward it, which means its charge will start from 0, which means if we just consider this one arrow, it should become -1. But notice there are two arrows moving away from that particular bromine location. So once you move one pair electrons away, charge increased by 1. So -1 plus 1 cancel each other out. There's a third arrow electron moving away, so it becomes +1. Okay? So that's a case to rationalize on the charge for that particular bromine. Okay? So this particular species is called brominium kind of ion. Okay? So this is something we will talk about in alkene chemistry. Okay? So this is a case with a neutral nucleophile. Okay? So how about if we do have negative charge nucleophiles? Okay? This nucleophile could either be neutral or it could be elective. So let's run into a few those kind of examples with a negative charge like nucleophiles. So as one example, I have this particular case. We have the negative charge of oxygen, and then what I have is a proton. Okay, so in this particular case, we find out we have a charged nucleophile reacting with a charged electrophile. Because both of those things are charged, this reaction will actually happen very, very quickly. So it's kind of almost an instant reaction. You mix it together, instantaneously, we're going to have the product. So of course, for the product, so notice we have talked about this many times already. Negative charge means there's a pair electron. Actually, oxygen does have more, so it has 3 pairs. We're just using 1 here. Okay, this pair of electron moves to the proton, and then we form the bond with each other. So that is our structure. Look at finally like a product. Oxygen has 2 bonds, hydrogen has 1 bond. Everything is perfect, low charge anywhere in this kind of product. And we try to rationalize. Here we have -1 to start with. We lose a pair of electron, and then charge decrease by kind of just, or charge will increase by 1, or we'll lose -1. Since we already have -1, we lose that -1, will become like a 0. Okay. For this kind of H class, charge will increase, charge will decrease by 1. So we start from +1, Once we decrease by 1, we have 0. So everything becomes 0. Okay? So this is a rather simple just step. Okay? So how about another case? If we do have a charged ion nucleophile, and then how about if we react with a neutral kind of the electrophile? Okay? So in this particular case, what do we find out? Of course, the same thing. Oxygen has a lone pair electron, and then this one will attack some places. So which particular place it attack for this molecule? You just need to analyze the charge a little bit. So here we have carbon versus halogen. Normally most typically halogens would have higher electron activity than carbon. So we would expect some partial negative charge on iodine, some partial positive charge on the carbon part. And of course, now we have the electrons. You'll definitely attack the positive part. Negative, positive, they attract each other. And then we try to maintain the valence for the carbon. So this kind of carbon iodine bond will break. So the products for this reaction will be CH3, OCH3, and then we'll have iodide. Okay? So electrons move to iodine, 0 goes to -1. Okay? Over here, we start from -1, electron goes out, it becomes kind of 0. And then we look at the final combination of everything. Here's the negative 1, here's 0. Combination is -1. Here we have 0, -1. Charge, total charge is -1. So it's balanced out. So everything is good and perfect. Okay. So this is what I want to show you, folks. Make sure just for this type of reaction mechanisms, give it as many practices as possible. Try to solve different questions, and then once you receive enough training, you're going to get a little bit better understanding about it. But the best way to learn it is to look at all different kinds of problems and try to draw those reaction mechanisms. For the rest of this chapter, there are more sections with different concepts for us to learn about. So I will delegate most of those the study to you. So just do check those sections 7, 8, and 11. Please study both my lecture notes and also the textbook. Try to do as much homework as possible to strengthen just understanding, and again, get any trouble, just make sure ask me for help. Okay. But I'll focus. The last thing I will talk about this chapter will be about sections 9 and 10. It's about the energy diagram of the organic reactions. Here we're going to use this particular reaction as an example. I've already talked about it. So isolene can add on to the HBr, and then we first step. Actually, it's two-step reaction. We first form the carbocation intermediate, and then that carbocation intermediate will combine with the bromide. We form the bromoicin as a final product. Okay. Reaction-wise, things seems to be reasonably simple, and we have talked about all those nucleophiles and electrophiles. Okay. So now is the time to take a look at this kind of particular reaction from the point of view of the energy. Okay. So notice we have three things over here. So let's focus on the organic part. We have organic starting material, we have this organic intermediate, we have this organic product. So with the three of them, each of them have different energy, and then we want to try to have this kind of energy diagram. It's two-dimensional. So we have this vertical axis and the horizontal. Horizontal just shows the reaction progress. So most commonly you can consider this as time. So time 0, no reaction. Some time pass, we begin to form intermediate. We give enough time, we form the product. Okay. So although sometimes it's still better to call it the reaction progress, because some reactions are reversible. So we could start from the product, times goes backward, we form some intermediate, we get into the starting material. Okay. So that will be about reversible reactions. Okay. But the point is that here we have this energy diagram, and then there's three species: starting material, intermediate, and product. So where are they? So our starting material is just an alkene material. It's reasonably stable. So let's say we have this particular state. Okay. So I'm just using this kind of line to represent this is actually our starting material. Okay. And then now we have the intermediate. Intermediate is carbocation. This is a neutral compound. This is charged ion. So for the related chemical structures, one thing that's common is that the neutral structure will always be much more stable than the charged counterpart. So when they're relevant to each other. Those two, of course, they're relevant. Both have 2 carbons and similar number of hydrogens. Okay. So when think about this intermediate, you should have a higher energy, so which is over here. That will be the intermediate. Okay? And of course we have our final product. So final product here is everything is measured by experiment. So what we find out is that for the particular product, it's going to be even more stable. Okay? So we have this product over here. Okay? So I have three states: starting material, intermediate, and product. Okay? So here there go three of those kind of states, and then we just begin to draw something like a diagram. So before I do that, I just want to show you like just some of those kind of first of all some of the summary. So first of all is about energy. Okay? So we look at those kind of the ions or molecules. They're relative like just kind of placed vertically. So of course that's referred to the energy. So here's some of those kind of summary. If a species has high energy, it means it'll be less stable. If something has low energy, of course, it'll be more stable. So out of those kind of three things we have over here, we find out our product is the most stable. Or in other words, we're going from our starting material to the product. We find out this particular reaction should release heat or release energy. Okay? So when you think about this kind of particular reaction, this should be one of those exergonic reaction. That's for this particular case. In other words, this reaction is releasing energy to the environment. Nature really likes that. Okay? So nature really favors this reaction, which can give out energy to the nature. So those kind of reactions are called spontaneous reactions. Okay? So that's why it's favored. Okay? So this is the first rule you need to know about. And the second rule about just drawing those kind of energy diagram is that we have those kind of states. Okay? So here's one of those kind of common, or one of the summary I kind of just obtain from myself. So over here that I'm putting the words. So this one, it may look like a little bit funny, okay? Doesn't really look like that much about chemistry, okay? So molecules, we don't consider them to be like humans have the feelings, okay? But here I just try to make it so that it's easier for you folks to remember, okay? So here a summary that molecules or ions in general, so those kind of the reactive chemicals, they really like to have some fun and they would like to ride the roller coaster, okay? So what exactly do I mean by that, okay? So over here, take a look at some of the states. We have our starting material, we have our intermediate, we have product. Okay? To think about one of the simplest way for the reaction to take place is that we start from our starting material, we take a straight line to the intermediate, because if you think about this is from mass, we think about as two of the points. Starting material is one point in the middle, intermediate is the point kind of over here in the middle. If we try to think about the shortest distance between those 2 points, of course, from mass you tell us the shortest distance between two of the points would be a straight line. Okay, we have a straight line going from starting material to intermediate, and then how do we get the product? We go here, we follow down. Okay, so supposing this should be very simple, like just starting material to the intermediate to the product. However, when people study the reactions, we find out the molecules never take this simple approach. So they never take this quick shortcut, and then just they really like to have some fun. Okay? So what really is that fun part? So we need to redraw that picture. Okay? So let's do a little bit of erasing and redraw. Okay? So for this particular reaction, intermediate, starting material, product, and intermediate. Okay, so here the reaction still more often followed by kind of curve pattern instead of just a straight line. So we're starting from the starting material, energy goes up, and then kind of falls down. Okay, so this is actually the energy diagram for this particular reaction. So now you find out it really looks like kind of more like a heel, like just going on. So why do I call it a roller coaster? So actually, it's a little bit more or less kind of when you try to visualize it, and then when you think about the actual roller coaster, it needs to make some kind of sense. Okay. Think about yourself as taking a cart. Think about some of those roller coasters, such as Disney World or like just or Universal Studios, or like just if you are really adventurous, just think about Six Flags. Okay? Personally, I can't ever take Six Flags. Okay, it's a little bit too extreme for me. Okay? But over here, like think about some of those kind of exciting roller coaster. Normally, you kind of take a ride, getting some kind of cart from like the bottom, and then the cart will slowly move you up to kind of point. And then that is the time when you build up some suspense, and then like, if you're really scared, and then just well, from my advice, like if you get scared, that's okay. So like just not everybody can handle that. Okay, and of course some people are bold, and you can probably take the most adventurous kind of rides. Okay, but like the similarity that we first take some like just to up to like highest point. That's normally when you think about like amusement park that's typically the highest point of that whole roller coaster. You get to the highest point, and then once you get over there and you wait a little bit for the people, like for the batch in front of you to finish the ride, and then once it's your folks' turn, you can find out the little bit push, your car begins to moving, so it will get rolling, and then just sometimes fall, getting down, and then rise up a little bit, fall down again. So sometimes it's just like a 360-degree kind of rolling. Okay, so for this energy diagram, it's not as complicated as that, but you can get an idea. Just go to the highest point, fall down, go to another higher point, and fall down again. Okay, so we have this process going from starting material to intermediate. That's our step number 1, which this part from intermediate to the product. That's another step, which is step 2 over here. Okay, so this is how the molecules like just take those directions. You never take those like just kind of the straight line shortcut. Okay, and then we look at those energy state. We find out that of course 3 of those things are very clear. So starting material, intermediate, and then just take the product. For any one of those, we just gave them some name. We call them like a local energy minimum state. Okay, there's 3 of them. Okay, starting material, intermediate, and the product. So what we mean by that is that locally you look at either here, it's a curve over here or here. Just think about it, it's kind of like the bottom of a hill somehow. So if you think about energy, so around here, this is the lowest kind of point. Around this location, around it, it's the lowest point. Over here, that's the lowest point. So those 3 are local energy minimum state. Those states are reasonably stable. Some of them, starting material, product, actually both are stable enough to exist. And then the carbocation is too much unstable, so we probably cannot really isolate it. But still, it should be able to exist for a short period of time at least. Okay? So that's our carbocation intermediate. Okay? Those, at least those local energy minimum state will be at least be able to exist. And then we look at the diagram. We have 2 of the heel points. One is over here, another one is at this kind of location. Okay? So for those particular the highest point, the top of the heel, we have 2 of them. So notice this part is come from step 1. So we give this kind of special name. We just call it transition state. So let's call it TS1. Right? So typically for the transition state, we use this type of symbol to represent it because this is from our first step. I would just call it TS1. For this kind of other one, that will be our transition state number 2. Okay? So we have our TS2. Okay? So this is actually how the reaction takes place. We have the starting material. You can think about each of the steps. This step 1 is a reaction. Step 2 is a secondary reaction. So for any of those kind of reactions, you find out it will always go through some kind of transition state. From starting material to product to the intermediate, we do not go there directly. We first climb up to a higher heel, and we just drop. Okay? And then going from intermediate to the product, it should be easy because energy is given out. It should be a spontaneous step. However, from intermediate, it does not take a free fall to the product. Instead, it climbs up again a little bit and then fall down again. Okay, so this is the typical feature for those steps. The molecules will kind of not go straight to this is what really this roller coaster is all about. Okay? And then there's some further details that we take a look at the energy from the starting material to the product, which is over here. If I try to extend the line a little bit, so over here we have this energy gap difference. So this is actually called delta G, the Gibbs free energy change for the reaction. It was mentioned in one of the, those kind of other sections, which I assigned the rating starting to you. Okay? But basically here we have the delta G. We find out from starting material to the product. Indeed, the product has lower energy. The starting material has higher energy. So the delta G, the energy change of the reaction, just equal to the energy of the product minus the G of the starting material. And of course, in this case, you can clearly see that our delta G is going to be negative, okay, because energy decrease. So actually, for the chemical reactions, we do want that Gibbs free energy change to be really just negative. When it's negative, it's favorable for the reaction. Okay, that's one thing you can see. Okay, another thing you can see that actually going from our starting material to the intermediate. So between those two states, let's draw some line over here. I wish you can see it clearly. Okay, so over here we have this energy. Okay, so from this kind of the bottom here to the top here. Okay, so this one we call the activation energy. So I just use the AE to represent it. Okay, so here we have activation energy number 1. And then going from this kind of intermediate to the product, we also have another second transition state. Okay, so the bottom here to the top here for this particular kind of the range. So this will be our activation energy number 2. Okay, activation energy number 2. Okay, and then from the picture, it's very clear that activation number 1. So we look at the gap. It's definitely much higher than this kind of second activation energy. So what does this activation energy mean, or what's its implication? Is that I'm going to erase some of this kind of the title. Okay. So this is the relationship between the activation energy and the speed of the reaction. So this particular reaction, as overall, is a spontaneous reaction. We release heat to the environment. Okay, that's something we can see from starting material to the product. But if we think about the particular steps, and then what we find out here, and also it's quite when you try to think about it, it's more or less kind of something which should be reasonably easy to understand. So such as you go here from the bottom hill, try to go to the top, we'll have a much steeper and a longer higher hill to climb. Of course, you can take a little bit longer time. Here we just have a short, very a small hill, and you just take a little bit of effort. You go to the top already, and you just fall down. Okay, so over here, apparently when we look at this particular step, so of course this one has higher activation energy, this one has lower activation energy. So if you think about the speed of this particular steps we have over here, we have 2 steps. So when you think about the rate of the reaction, so over here, the step number 1 would be much slower than number 2. Okay, so because the second step is much easier, first step is very hard. Okay? So we will not test further details about those kind of the steps and then reaction kinetics. Okay, how fast, how slow reaction goes is called reaction kinetics. Okay, but when you try to some of our homework, occasionally they will mention this kind of the rate determining step. Okay, so over here we have 2 steps. So we're going to find out step number 1 will be something which is called the rate determining step. Okay, so this is a detail which we will not really test in our exam, but since our homework has that, I just want to mention it to you. so that you can have a new better understanding. And when you look at it, it's also could be kind of somewhat counterintuitive. Okay, we have two steps. This one basically is slower. This second step is much faster. So why the slower reaction will determine the reaction? So the way to rationalize this you can think about our humans. So think about some of those relay race. Okay? If we do have a relay, there's a team, and you and your teammates are gonna take in turns to run, and you're gonna find out if you have some fast runners. Of course, you have a better chance of winning. But you're gonna find out eventually, if there are two teams or many of the teams, you find out it's slowest the player of each team will really make a dramatic difference. Okay, so such as if you do happen to be a very, very slow just runner, and you can drag the foot of your whole team, and then even your other teammates may be very fast, you could be if you're not really good at running, you could drag this whole team down and not winning the race. Okay, so over here it's really this slow step takes time to build it up. So as long as we get to an immediate, it will get to the product almost immediately. So when you think about the control for this reaction, so this is the harder one or slower one, so that determines the speed of the whole reaction. So we call this step number 1 over here, the rate determining step. Okay? So this is just one example. We have other type of energy diagrams, but in general they do follow this similar pattern. So one of the most common things that from one state to another stable state, we always climb up a hill and then fall down. So, and also if you think about if it's not this particular reaction, if it's other reaction which can be reversible, so let's think about we go from this side, from the right to the left. So such as you see, if we want to go from here to here, we find out we also need to climb a hill. If you want to go here to here, we need to climb another hill and fall down again. Okay, so this type of feature is very, very common. So that's why I said molecules like to ride the roller coasters. Okay, so that's pretty much what I want to talk about for this whole chapter. And then just again, try to have as many practices as possible. Okay, and then just some of those concepts which we can pretty easily construct a question. Some other ones is probably will just be for information. So in terms of testing purpose, so this particular chapter will not be too much focused. But some of those details such as those arrows, electrophile, nucleophile, some details about those energy, make sure you get that. Okay, we'll not have too many questions, but this chapter will surely be tested in the exam. Okay, if you have questions, do check with me.